welcome Benjamin Heilbrunn. He did his PhD, actually as an external PhD in our group. He worked several years at the SAP lab at Falkenbrunn and is now in Potsdam in the Innovation Center at SAP. And he will give us an insight into a path from a big monolith like this R3 S4 system. Not sure, I think S4 is what I have to say right now. This is the current version of an enterprise relationship in the resource planning system, and how this can be translated and transformed somehow into a native cloud application. So
this is how we try, yeah. Good, yeah, hello everyone. As Thomas introduced, I'm Benjamin Heilbrunn from SAP. Thanks for the very nice introduction. And today I want to talk a little bit about our journey from, as he mentioned, having an ERP system that is kind of already in development for many decades, thousands of developers, of course with continuous innovation, but now facing a big challenge of kind of being pushed from an on-premise system that is usually run by customers on their own hardware, or at least on their controlled infrastructure, to a system that is provided in the cloud, also a software as a service, and that kind of leverages the advantages and opportunities that you can have when you run systems in the cloud in a maximum manner. What I plan to do today is basically going through this 5 steps. So I will start with a little introduction of myself, the company I work for, to give you a little glimpse of what we are doing. Then I will dive into our flagship ERP product, which is called S4HANA, and basically how it evolves or is planned to evolve in the next time. We already understood cloud is the direction to go, so I will talk a little bit about what does it actually mean to build cloud-native software, what do we kind of expect from it, what hopes do we have there. Then, in the last parts, I will basically cover how we currently approach this challenge of transforming this monolithic ERP system into a cloud-native ERP system that leverages the cloud advantages. And if I have the time, but if not, also no problem, I will talk a little bit about the new challenges that we face now once we are in the cloud, and some ideas how we can approach that. If you have any questions on the way, or if you feel like totally disconnected from what I'm saying, I think it's okay if we make it interactive. Stop me, we can have a quick discussion. We have to see if there are maybe too many questions, and probably I have to hurry up. We can try it in that way. Good, let's start with a little introduction. Thomas already did it very well, actually. My background is in computer science. It's what I did in my bachelor. Then I studied business application architectures in my master. I moved here to Dresden, started my PhD with SAP Research back then and the TU Dresden. And since 2016, I'm working at the SAP Innovation Center in Potsdam, mainly in cloud projects. In the beginning as a developer, now also in a kind of a role like a technical lead or architect. This is the place where I work with the biggest part of our team. It's located in Potsdam at the Lake Jungfernsee, so if you know the geography there, you have a lot of water. We are close to one of those lakes. The kind of branch is quite young, so it exists since 2013. In the beginning it was one building, now for a few years already we have a second building. And compared to the usual size of locations of SAP, we are actually quite small. We have around 250 people working there, maybe now a little bit more, 300 or so. But that does not mean that it's not an important location, because, for example, one of them is our CTO in the company. And that's also one of the reasons why a lot of the innovations that are relevant within SAP come from Potsdam. The way how we build cloud applications, for example, right now, but also how we want to improve, evolve that, is strongly influenced by what we do there. the way how we interact with our ecosystem, yeah, how we define the developer experience in our domain is strongly influenced by what we do there. And also a lot of the, let's say, new hype topics, yeah, like machine learning, blockchain, serverless computing, or also partial trends like Kubernetes that are relevant in certain contexts. They are kind of relevant in the context of our work, and we try to understand how can we best make use of that in our business domain. Now a little bit of background from the perspective of SAP, yeah, for the fact that we are an IT company. We are extremely old. We were founded in 1972. We have, like Potsdam, more than 100 development locations worldwide, and probably already now more than 100,000 employees. So this is a number from September. We are serving almost 500,000 customers, also around the globe, including the most valuable brands that you can imagine, also 29 of the 30 DAX companies. And maybe also interesting, if you look at how we earn our money, right now we have a revenue of around 25 billion euro. A fifth of that, which is a significant number, comes from cloud software, but it's only a fifth so far, and we plan to increase that steadily. So the importance of cloud software is really prevalent for SAP. From research perspective, we are also quite active. We got granted around 700 patents in 2018. It's a recent number I could find. And we are not totally isolated in the sense that we just do our stuff for our customers. We also have a very vibrant ecosystem with around 20,000 companies that act as partners and multipliers for us. Good. So I hope this gives roughly a picture where I come from or which company I work for. Now let's talk a little bit about the product, which is in the center of this cloud transformation that I will cover later. It's called S/4HANA, and as already briefly touched, it's an enterprise resource planning software. And so who knows what ERP is? Okay, very good, then I will quickly explain it. It's basically a piece of software that helps companies to run business processes with the help of IT. So, for example, finance, creating invoices, handling invoices, and so on. Sales, manufacturing, asset management, and those domains, they kind of have requirements for, I would say, hundreds or thousands of applications in companies, especially if they're big, to efficiently execute, and also in compliance to regulations and so on, to execute those processes. And if you as a customer want to adopt S/4HANA as of today, you currently have two options. We are kind of in the verge of this, or in between this on-premise and cloud world. You can do both. You can either buy a license and install it on any premise and then take care about it yourself, more or less, about the life cycle of the product. Or you say, I buy a subscription, I pay for it monthly or yearly, and SAP, please provide me the software. I just want to make use of basically that. I don't want to care about the management. And also very important to mention, it's a standard software, so you configure it. You have plenty of options to customize it to your business needs. But for, let's say, cases where you want to adapt it to your specific needs, where you maybe also want to differentiate from competitors, if you have specific processes and capabilities in your company that you need, then you can build extensions that integrate to it and that kind of use the interfaces that it provides to kind of realize this customization, specific process that you want to have. And usually those extensions, they are already being built in the cloud. So of course it's also one of the factors why moving S/4HANA as a product itself to the cloud is also kind of interesting for us. Architecture-wise, where we are standing today, no big surprises. It's a classical three-tier application, the monolith. So we have UI, which is accessible via the web browser. for those who already used an SAP system longer ago, I'm not sure if anyone is present, they maybe know SAP GUI, which was like a native client, like Excel you start on your PC. That is not existing anymore, so we completely transformed to this web front ends. On the application layer, there's a proprietary application server, which is executing ABAP code. It's a 4th generation language. I think one of the few ones which were successful. And if you are running S4HANA in the cloud, that part is already completely managed by SAP. And underneath it, there's also a proprietary database, which kind of has a special attribute that it's completely in memory, which makes it kind of well suited for transaction as well as analytical processing, which is called SAP HANA. And of course, that is also managed by SAP if you buy the product in the cloud. Yeah? Good. So, yeah, as I already mentioned multiple times, S4HANA is a piece of monolithic software, and we want to change that, but let's quickly talk about why we actually want to do that and where the problems or the trade-offs are between monolithic and highly modular distributed software. Because I think we all build monolithic software. I mean, if you start building something, it's in the beginning always a monolith, more or less. And that actually has a lot of advantages because in the beginning, what you want to do is you want to have everything in one place. So you, if you want to understand what your software is doing, there's one code base, you can look into it, you can follow references. For example, if I call this function, how is it implemented? If you refactor it, you have refactoring support in your IDEs, so your IDE can do the refactoring for you. It knows all the places where something is used. Usually it can detect if you broke something, for example. If you want to debug it, you can basically also follow all the traces in the code. For troubleshooting, also this kind of locality of everything is helpful because you have the truth, so to say, directly in front of you. So there's nothing bad about monoliths, but if you look for certain qualities, they start to become problematic, and also for a certain scale. And this is something I want to tease a little bit now in the next slides. So what do we actually want to achieve for our customers, or what does the market demand from us that kind of pushes us away from this monolithic architecture? First of all, there's a strong need for agility. That means markets are moving quickly, the demand of customers is often kind of quickly changing or even unknown for a long period of time, so that you cannot really kind of plan for years what you want to do in your software and how you want to build it. Just build it and then release it, it's fine and the customer's happy, but rather you need to go in quick cycles. It means you build something, you evaluate it early, you collect feedback, and based on this, you then make adaptations to your plan. And only if you can do that quickly, you are able to survive in today's markets. Then, of course, like everyone in the industry, we are also a company that needs to earn money. Our partners, our customers need to do that. So the cost of building software needs to be as low as possible. You want to achieve a low cost of development. Another thing is you want to be highly available. So I don't know, many decades back, maybe it was acceptable to turn off a business system during the weekend to make an update. Today, everyone has a corporate mobile phone. We are used to Facebook and all the other wonderful web services or online companies that are all the time available. And I would not accept it, and many other people would not accept it if they cannot maybe do a vacation request on the weekend, also because the system is gone. I mean, this is maybe still tolerable, but I want to check my emails. I want to be basically able, if I want to do business also for example, at the weekend. So availability is really critical. Another thing is elasticity. I want to be able to, for example, do my payroll run at the end of the month in a way that I pay for the resources that I need for it, which might be for a certain point in time really a lot, but without the need to provision this hardware all the time just to kind of be able to handle this spike that I have only once in a month. That is simply a waste of money. So I want to be able that my system that I provision and the hardware that I need for it, or the resources that I need for it, that it quite accurately reflects the actual demand that I have. And lastly, this is maybe the overall topic and also for elasticity, I want to have low operational costs. So the costs for having that system up and running, serving its needs should be, of course, as low as possible. And when I kind of manage to optimize against those qualities that I quickly showed, then of course I can offer a good pricing model for my customers, attractive prices, and also good SLAs in the sense of terms for my services, so that they say, yes, this is something where I actually want to pay money for and my business will benefit from it. Good. So now let's go back to the monolith. Obviously there are some problems with monoliths if you think about those qualities. One is illustrated here. In a monolith, as I said, you have basically access to everything. Yeah? So you can do more or less a reuse at any location, and this is also what happens. So imagine an ERP system where you maybe have, we'll use the term orders as a domain, customers as a domain, finance and users. And while they maybe are quite separated in the beginning, what happens over time is, I don't know, when you implement some order functionality, you find something in your customer model or customer function that is interesting for you. So you just reuse it. It's efficient, right? So just do it. Or, I don't know, finance and orders. You start to widely reuse stuff. And over time, and now we are talking about years and decades of code evolution, you have a system that is basically what we often call a big ball of mud. So it has such a high level of coupling and interconnectedness inside itself that you can more or less just look at it as a whole. You cannot easily take things out. For example, evolve one module independent from the others in the sense of that you say, okay, I want to change something here, I want to modernize it because suddenly 10 others in the company are affected from your change. Or you say, I want to take the payroll functionality out and scale it independently on some infrastructure because it's so interconnected to other pieces of your software that you cannot simply do it. So you run into a lot of problems with this kind of architecture. And this is also reflected in the kind of release schedule. If you look at it today, what we can do is, with already a lot of effort, the maximum we can do is that we release new versions of S/4HANA in the cloud every quarter. Speeding up that process is today not feasible, or kind of you could maybe, but at some point in time you would drown in overhead. And I mean, I already touched some of the challenges. Here's also again a summary. If you look at it from development perspective, you have this coupling that I explained. So you have to talk to a lot of people. There's technical coupling involved. Another disadvantage of a monolith is that you have a homogeneous technology setting usually. So I talked about ABAP, right? So whenever you want to build something new into that monolith, you're somehow constrained by the already existing code. You need to use the programming language, maybe also already existing frameworks and libraries and so on. And you may miss out on the opportunity to leverage something that might be able to solve your problem better, like open source libraries that exist in some language or so on. So this is also a disadvantage. Then, with a big and longly grown legacy code base, you also very often have still a lot of manual quality assurance. So I'm not sure how you basically approach software development today, but I think test automation is probably a very important topic, which is also taught for software development or software developers. But if you look into the reality, and especially in the long reality back, full test automation is simply not there. So on this code basis, it's typically or you typically still have a lot of manual quality assurance. It means that people really go to the real system, which is running somewhere, which can already be in high effort, and go through manual checklists, like does a certain process work like I expected? And it's of course costly, slow, and problematic in the sense that you want to quickly and confidently evolve a code forward. And yes, what also still happens, I think, is mentioned earlier, that in order to manage such a big monolithic system in development, specialized departments are being created, like a development department and a test department, because they kind of specialize in these functions. This increases the amount of overhead in the sense of that you have to hand over information, but also information loss, because the test department basically has to test something they didn't write, and in that way, yeah, the system overall for evolving such a piece of software gets also more inefficient. So this is on the development side. On the operation side, in order to bring those systems alive, very often you have procedures that are 100 steps long and also that have to be manually executed just to get a working instance. So these systems, they are so complex and they're so big that just the effort of setting them live is incredibly high. Then, if you think about it from a failure perspective, you have this big system, now something goes wrong. The system, of course, even though there might be partial failures, but as a whole, it can happen that if there's a small issue, it basically takes the whole system to it. Even though, if you would have designed it differently, maybe it would have just meant that a slight functionality is not present or not working anymore. Some users would have been affected. It basically has a dramatic effect on your business. Then, on the topic of elasticity, and also taking into account the size of the system, it means that, of course, you cannot really size the hardware to your needs. So you're always in a situation where you say, okay, I throw enough hardware at it so that I can handle all the peaks that I have, which means you overpay, or you kind of make a trade-off decision, say, okay, I accept it if my system is overloaded from time to time, but then you're also more or less unhappy, or you at least have some unhappy users. Yeah, and so in conclusion, you cannot elastically scale and in the end also not achieve the kind of pricing that you want to have, that is on-demand based, so that your customers say, like, yeah, this is something that matches my business value and I want to pay for it. Good. So luckily, we are not the first ones who are facing those challenges. There are other companies in the industry who were in exactly this situation before, and they have names that you would maybe not imagine when you think about the problem that I just described. One of them is Amazon. So they started building their shop in the beginning also as a monolith. They were successful with it, but then their growth and success suddenly became to a risk because they exactly ran into this situation. So people were stepping on each other's toes when they were working on the software. So adding a feature here might cause a regression at some other place. They had incredible problems with operating it to exactly the reason that there was one department who had to take care about keeping the system up and running for the customers, but there was another one which actually built it, and they also had conflicting interests. And what they did is they basically switched to a cloud-native way of building their platform and the shop, and adopted also things like DevOps, also strongly driven by Jeff Bezos back then, which kind of made them overcome these challenges, and as we all know, it's a very successful company these days. Probably they did the right thing. And that's what we basically now also want to repeat. We want to learn from that. We want to do the same thing with our, of course, way older software and also way larger probably. So we want to take this monolithic, strongly strongly influenced design by the on-premise way, how it was provisioned software, and bring it into the cloud, make it an offering which leverages cloud principles as much as possible. Just to give here again the example, we want to make it very available, elastic, drive down costs, make it flexible and also allow people who are involved in the development to innovate the parts where they are working on and kind of in that way make it also successful in the long term. This means basically that we have to make a decision or have to make decisions how we want to do that. Either, for example, rewriting it completely or approaching it iteratively. The first approach already kind of, I don't want to say failed, but didn't succeed. Several years back, SAP had a try to build an ERP system from scratch for the cloud. It was called SAP Business by Design. It was at least not the success they hoped it to be. Right now it's actually running quite okay, but only over the years. And that's why this time for S4HANA, we decided that we want to approach it iteratively, which is, I think, also a good way. And in that way, we want to, in the long term, get rid of, or at least shrink the current monolithic code base and build up a cloud-native code base. Good. Up until this point, any questions, confusion? Very good. Then let's talk a little bit about cloud-native and what it is about. So there are actually several definitions for this term. I think for our purposes here, I will use two. One is a little bit more concrete, and this one here is a little bit more abstract. I think it covers it well. So there's a Cloud Native Computing Foundation. Maybe some of you heard the term already, which also curate a big landscape of technologies that help you to understand what is actually considered cloud native and what role does a certain technology play if I want to build a system, how can I leverage it? And the Cloud Native Computing Foundation defines it as basically, well, defines cloud native technologies as technologies that empower companies to build and run scalable applications in cloud environments. So their emphasis on scalability, and they talk also a little bit about the qualities that cloud native applications usually have. So they are loosely coupled, they are resilient, so they can tolerate failures to a certain extent. They are manageable, observable, and usually they leverage a high level of automation, so efficiency gains. And with that, cloud native applications basically allow engineers to confidently make high impact changes without much pain. That means this evolvability is assured in software. Another definition that's a little bit older, I guess, comes from Pivotal, which is one of the big companies in this domain, and they kind of already provide a, let's say, more pragmatic definition to cloud native. They say cloud native is if you build your software according to DevOps principles, if you use microservices that run in containers, and if you deliver them with continuous delivery. And what I want to do is I want to go through these 4 pillars now in the next minutes to give you an understanding what's behind them. Maybe question here, is this somehow covered also in other lectures that you have? Good, then I will not go too fast. So DevOps is basically a movement in the software industry that stands for development and operations. And the idea of bringing this together and establishing end-to-end responsibility in teams instead of having this separation that you often face in today's, or at least companies before the DevOps movement became important, also prominent, so to say. Yeah, and basically what DevOps says is that you should focus on 3 principles. You want to quickly deliver working software to your end users. You want to establish quick feedback loops so that you discover problems early, as long as they are still cheap to fix. And that you basically establish an organizational culture where you say, I want to continuously learn, I want to evolve myself as an organization, challenge myself, and in that way kind of disrupt myself before others do it. Always in small portions instead of narrowly following a plan and then someone else does it. The cool thing about DevOps is there's actually plenty of research around it. Also by an organization which is called DORA, I think DevOps Research something. And what they found out is, by doing a lot of surveys and data analysis, that those companies which follow these principles that I just mentioned are way more successful than those who don't. And they have these KPIs. If you separate well-performing, from an economical perspective, business success. If you separate companies into those who follow those principles and those who don't, and you see that KPIs like how often do I deploy my working software, flow of work, that they are significantly higher, or that the way or the time it takes to build and deliver a feature is way higher. And also the time for being able to restore from a problem that I detected is way higher for those companies compared to less successful ones. Good. Now let's move over to microservices. Microservices basically define the idea that you build your software in small autonomous services that are also independently evolvable and also independently deployable. You can change them individually without having a large effect on the overall system. That way you can have this loosely coupled business domains that together form the business solution that you want to bring to the market. And yeah, one of the advantages is that you have a higher flexibility than with these monolithic applications. On the other side, of course, you have to pay the price of for the fact that you now have a distributed system. This is one of the advantages of a monolith. Everything you call inside it, or usually everything that you call inside it is more or less just a local call that you do inside the hardware bounds of one node or so. And therefore also much less can go wrong. You leverage microservices basically for three benefits. The one thing is you can choose technologies quite freely. So for one microservice you might use Java because the programming language and its technology ecosystem is exactly what you need to doing the job. And for some machine learning rich microservice, maybe you want to use Python because there you have the tools you're looking for. Then going back to the Amazon example, with microservices, you can also reflect this organizational alignment. So I'm not sure if someone already heard the term con-based law, which basically states that the interfaces of software in the end are always more or less a projection of your organizational structure. And therefore the conclusion is that you should, of course, align them. And with microservices, you have a way how you can also reflect this very well. So you don't have this monolith where everyone is fighting with each other in the same code base, but rather you have microservices that are reflected to teams, or kind of where individual teams are working on them. The teams talk about interfaces, and everyone is doing his job and implementing it in the best way possible. And for example, Amazon, they really take it to an extreme. If you talk to teams there and ask them, like, how do you define your goals? It's basically the interface definition, which they need to fulfill as a team. That's their goal as a team. And lastly, if you have small units of your service, then you can, of course, also easily scale parts of your system to the demand that they see. Take the payroll, you have a payroll service, you can, at one point in time in the month, scale it up, and afterwards free the resources by scaling it down again. Then the second last point is containers. I think every one of us, or at least I hope and assume that we already used containers, right? Very good, nodding heads. So basically this is a way of packaging software, making it kind of self-contained and executable in any environment, which is of course nice in the cloud, yeah, because you can almost everywhere where you have a container runtime, just throw in your software and say, please start serving this. So just a necessary prerequisite to efficiently provide all these qualities that I discussed earlier for software. And lastly, continuous delivery, which is basically a practice that brings me closer to the ideals of DevOps. Helps me to sort of say implement a part of it, which basically describes the idea that I completely automate my process of building, testing, and validating my service before then also automatically deploying it for my end users. So where I previously maybe had this hundreds of steps and maybe also unreliable human-driven processes where someone was manually producing and then deploying the software, I now have a repeatable automated process in the form of a continuous delivery pipeline that pushes out my service and even maybe takes care to automatically activate it. First for a fraction of the users, then for more users, and then finally if everything succeeded and there are no unexpected problems for everyone. And yeah, of course this is then also an enabler if you think about the metric that we saw earlier, quick time to recovery, to be able to quickly change things even if they went wrong. Of course I want to prevent errors from happening. I want to discover as much as possible by this automated validation process. But I don't have to be so afraid anymore from causing a problem, because if some customer calls, and for example, we also had that in our team multiple times already, and says, yeah, usually you have smaller problems that kind of slip through pipelines, like there's a glitch in the UI. Gives you the information, what's wrong, you quickly investigate it in a production system, you provide a fix, goes through a quick review, you merge it into the main code line, and then 1 hour later, it's already deployed. And you can confidently call the customer and say, hey, we took care of it, and it works again. Good, so that's the understanding of cloud native that we have. Now let's talk a little bit about the journey that we go through for transforming the ERP into a cloud-native product. Yeah? And as you can imagine, it's not easy if you look at decades of code that of course continuously maintained, but it still has this legacy. How do I now start turning this into a cloud product? Yeah? You should not make naive decisions in the beginning. And there's luckily also already, let's say, a body of knowledge available, what works and what doesn't. Yeah, so we don't have to or we don't have to invent everything ourselves or experience everything ourselves. We can also follow certain, let's say, industry experiences. And one of the general guidelines is to start with taking some functionality in the beginning that is more or less decoupled from the monolith. Think of it like a satellite functionality. So it provides value for a certain use case, but you don't necessarily need it for the core processes. For example, creating an order process. Yeah. So one of the requirements or criteria is, for example, it should not necessarily need an own data store or a large, let's say, or own technology stack. So a small client-facing application that provides maybe some new features is sufficient for this first step, because what you want to do in the beginning is not to start this, or you don't want to dive too deep into the architectural transformation, but rather you want to make yourself and the team familiar with this new cloud world and the challenges that come with it. Yeah? So how do I now actually operate cloud software? How do I deploy it? Yeah? How do I write my own continuous delivery pipeline? All those things will be new. The team will be quite overwhelmed, so we don't pick too hard problems on the architectural side. is basically reflected here in the picture. Yeah, on the bottom you have the old monolith, now abstractly represented with two components, where you then say, okay, I provide new applications on top. They kind of act as abstractions or proxy also to some of the capabilities that I still serve from the monolith. And I also, for example, still do synchronous calls or even direct data access to build my application in the cloud. And let me quickly check if I forgot something. Of course, there are still disadvantages with that, since it's just a warm-up exercise, for example. You are still very highly coupled into this world. You provide something fancy, something new, maybe also something scalable up on top here in the cloud. But here you have still a full login into your monolith, maybe even the database, and therefore you're also coupled to the life cycle and many decisions that happen there. One example for this is SAP Real-Span. That was the product basically where I started working on when I joined my team in 2016. Takes a lot of the existing, or some of the existing functionality from S4HANA and implements it new in a very attractive manner for end users. Yeah, so there's also thought about a lot about it from a user experience point of view. In particular, looking at expense items of a cost center. So I'm a manager, I have a certain budget and expenses that are created in multiple dimensions. And with this app, I can look into those expenses and start analyzing them. It's basically an app which just retrieves data and then provides some analytical capabilities. And so this is something I could also still do before Real-Span, but now I can do it in a more modern and more user-friendly manner. And on top of that, later on, we also, this will also be shown in some of the later steps, in Real-Span we also started then building more innovative features into it, like an anomaly detection which uses machine learning, or an integration into other SAP products that, for example, helps to analyze HR costs, which are not usually reflected in an ERP system. Yeah, and with Real-Span, we did exactly this exercise. We started to play with the capabilities and opportunities that you have in the cloud. Yeah? So compared to the classical S4HANA stack, it was built with full multi-tenancy in mind. Means that one single instance of the application, which maybe has a baseline resource consumption of 1 or 2 gigabytes of RAM, can serve an arbitrary number of customers, users who are active. Of course, not arbitrary in the sense of that it does not need more resources if more users come, but up until this 1 gigabyte or 2 gigabyte is full, it can kind of acquire more user sessions, and then if even still more users need a Real-Span, then you can just put a second instance beside it. In the classical world, what you would have done is you would have created one Real-Span instance for every customer, independent from the demand that is actually present for Real-Span. Of course, due to the fact that everyone would have had his own on-premise installation, and here, since we are in the cloud, we have one central place where we can optimize the resource consumption. Then we started to build up a lot of knowledge on continuous delivery and automation. So what we did is basically delivering every change that we made to the main code line into the cloud. And in the beginning, the quality assurance process was maybe not that sophisticated, but we acquired more and more knowledge. We also wrote more and more tests over time. We fully automated that. And by doing it basically now, still every time we evolve Real-Span, we leverage this codified capabilities and knowledge to ensure that problems don't pass through or errors don't pass through, and that the delivery goes smooth and fast. And just to also maybe give a nice number here, I think probably it's already higher today. We delivered RealSpend in the first years many thousand times into production. If you compare it to a quarterly release cycle, we could have done just a very small fraction of that. And imagine that you are able to acquire feedback every time you do an iteration. Even in the early phase, you may have a daily call also with customers that you collaborate with to innovate and breed your product. And this is an incredible advantage from a competitive side compared to classical software development that you do on-premise or in slower release cycles. Then the last thing we learned is how you build cloud software in a resilient manner, because now you have the network in between software components, and a lot of more failures can occur, and in RealSpend we try to circumvent as much as possible, be designed for these problems that can occur. This also led to the necessary knowledge in the team how distributed systems can be designed or should be designed. And of course, also to illustrate this here, since we now made this move out of the monolith, where you have certain boundary conditions, how you can implement the software with those applications that we started building in the cloud. Of course, there are more examples like RealSpend. We were able to leverage a large open source ecosystem. You probably know a lot of those technologies here that allowed us to efficiently progress and also achieve a high developer satisfaction and a good developer experience on that way. Good. So on the other side, there's a price to pay. I think I touched that already from time to time. So we are now in a networked environment. We have things like timeout, congested networks, more or less arbitrary failures of nodes from the perspective of an observer. We have clock issues, memory leaks that can occur, human errors still, even though there's, of course, a lot of automation in place, and complicated troubleshooting and diagnosis environment, because everything comes together as a whole by, let's say, many individual, also separated components. RealSpend internally also already kind of quite separated some of its work in several services, and now when something goes wrong, you somehow start to look through multiple locations and you somehow try to correlate what went wrong, which can be problematic. And of course, there's the cup theorem, which looks different on my screen. So there are no circles, which basically says that for a certain point in time or a certain functionality, a piece of software in a distributed environment can only optimize either for availability and in the fact of a partition tolerance or consistency. And of course, what you usually want is you want to design for availability. That's where the team also needed to kind of get familiar with new technologies. And one of them is, it's also design approaches. And one of them that we introduced is, I will come to that in a second. First, I will show one of the new failure scenarios that can arise in such an environment that kind of you would not have to solve earlier. Here, what we basically see is a multi-tenant environment. We have here, for example, RealSpend as the outer box. It's running in a process. Now we illustrate here a shared resource on the example of threads. So for incoming connections, for a RealSpend instance, you have a certain thread pool available from your application server. And in this RealSpend instance, we are currently serving 3 tenants, which each have a connected S/4HANA system, no matter if it's in the cloud or on-premise. It's connected to this real-sprint instance. And what can now happen, and also happens from time to time, is, for example, that one of those connected S4HANA systems faces an issue. For example, the network gets slow. The requests from tenant 1 to his S4HANA system start queuing or piling up. And of course, we have synchronous communication going on. Our connection thread pool starts to allocate more and more threads that are waiting for the requests which are stuck on S4HANA system 1. This problem persists for a long time. At some point in time, the connection pool will be full. And suddenly also the requests of tenant 2 and 3, which are working well so far, will not be handleable anymore because simply this application server, which is used by all of them for hosting real-sprint, does not accept any incoming connections anymore. Now what happened is you had a cascading failure. That means the problem of one tenant here affected the user experience of other tenants. And that's what you want to avoid, because it's actually not logical. A problem of tenant 1 should also, or can affect tenant 2 and 3. And for this, you need certain, let's say, design principles or also reuse functionality in your software to avoid such problems. Just to also illustrate why this is very important in the cloud, if we have a multi-tenant side-by-side extension, like real-sprint, that connects to the 30 S4HANA systems, and each of them has an uptime of 99.99%, which is really, really good. So it's probably not the reality. Then we would already kind of reduce our real-sprint uptime, assuming that the scaling failures would occur, to a maximum of 99.7%. So no matter how well the rest of it works, just by the fact that 30 systems are connected and each of them has this availability, statistically our availability would go down to 99.7, which is not that good anymore. Assuming that you have way more systems which are integrated in that manner, then of course the availability would even go down further. And this is also now illustrated with time. You would have more than 2 hours downtime per month with this 99.7% availability. Good, so what can you do about it in a synchronous scenario, which you will probably have in the beginning quite often? You need to look for certain resilience patterns that help you to isolate those problems or circumvent these problems. And what's typically being applied here are bulkheads, timeouts, circuit breakers, and fallbacks. Usually you can kind of pick from, or usually you pick from multiple of those options for certain integrations. Buckets means basically that you isolate requests on certain thread pools. Yeah, so for example, every connected S4HANA system and the requests which are made to it will be dispatched to a thread from a limited sized thread pool, and that thread is then basically working on the request. If there are requests piling up, that thread pool will be exhausted and no more parallel requests will be started. So you kind of limit the resource consumption. Then you need to also actively fail things in such a system. So you start to kind of set timeouts on certain parts of your work that you do. You establish circuit breakers. That means you you don't try to do something that failed earlier and that has a low likelihood of succeeding. Yeah, so for example, you had now 10 requests to one S4HANA system that failed due to timeouts or whatever, and there's an 11th one, and the likelihood that this one now will succeed is of course low. So what you do is after the 10th one failed, for example, now you trip a circuit breaker and you say, no, please don't try this anymore. And for the following request, you basically don't even try it anymore. In that way, you also don't create load or additional load on your application as well as on downstream systems that are facing trouble. And lastly, if something went wrong, in some cases it might be reasonable to provide a fallback. I don't know, these things, they come from Netflix, or they were a lot promoted by Netflix. And what they, for example, do is, if your recommended movies can currently, I'm now imagining a scenario, if they cannot be calculated exactly on your preferences, then they show you a generic list, which is calculated on the average of all users. Also, and they just have a static list that they then provide in such a scenario. So can be reasonable in some scenarios. In the business context, you will rarely make use of that, but you should still have it on your radar. And the last pattern, I think we all know it, is also caching, which of course helps you to kind of not create any load at all. If you already know the answer, or if you can kind of take a certain answer that you got some time back as still valid, then you can directly provide that to your consumer, or the one who made the request, and in that way gracefully decrease the load on your overall system. Now, a little reference to what we now do as a team. This story is of course about whole SAP. What we do is we help people also in scaling this learnings that we generated into the whole ecosystem. So we are not only a team who builds applications, but also we enable our internal as well as external partners and stakeholders to get embarked on that journey of building cloud extensions and succeed in their development. So we multiply the knowledge that we generate with books, or a book that we wrote, an online course. We help to create artifacts that help people to quickly create new projects. Then a lot of the patterns that I just showed, or actually all of them, are available via some reuse libraries that we provide that are already specialized for the SAP use cases. And for continuous delivery, we also provide ready-made toolkit that allows our customers and partners to set up continuous delivery infrastructures and also consume already programmed, reusable, ready-made pipelines that are attuned to our project archetypes or skeletons, so that they can, from day one, start doing continuous delivery in their projects. This is also quite interesting work, because you always work on applications with the idea of multiplying the knowledge that you generate for this ecosystem, so that this transformation can go faster and be successful. Good. Now, what we have is, you remember, this satellite application that now integrates somehow to our monolith, still with a very tight coupling. What we now want to do in the next step is we want to increase the independence. We want to shift some weight to our cloud service. And what then happens is that you kind of start building new capabilities into them, maybe also kind of reduce the coupling on the database, maybe establish new service interfaces, so that the integration between your cloud service and the monolith gets, we call it anti-corruption layer, or it's called anti-corruption layer, that does sound translation between what you have in your old world and the new world, and by that, so to say, the new world gets more independent, can also start working more standalone. Yeah? In this case also, for example, it's then imaginable that the services that you build start integrating with even other systems, not necessarily the single S4HANA ERP system, but you could imagine that other either similar or even completely different systems get integrated into this landscape. And in that way, you kind of can already reduce the communication or the coupling that you have in your monolith. And so the architecture starts not only to get extended by some satellite system, but you can improve it here and reduce the pain that you have here. So here's one example how real spend looks like. So for S4HANA, let's start maybe in the beginning. We have the real spend front end on top, which then basically communicates to a RESTful service layer, and here we basically implement the integration to all relevant systems. So it does not only integrate with S4HANA, which is one of the data sources, but over time we also added an integration to the HR system. I mentioned it earlier, if you remember. And what it does is basically it acts as a facade that distributes work to those systems. It collects all the expenses and aggregates them back in the graphs that we showed. And for the SuccessFactors case, it's also, so this is our HR system in the cloud. It also gets actively integrated, so it doesn't only call into the system, but also is notified via events and kind of becomes more or less an integral part of the architecture at this part, because it already starts to kind of store and replicate certain data for capabilities that it provides for its end users that have not been there yet, while here we just kind of on the fly retrieve data. Good. Then there's step 3. This is the last one that I'm showing you, where you then actually actively push what you want to do. You start to shrink the weight of the monolith actively by retiring functionality here. And what you do now is really you give up any lock-in or coupling that you have, for example, against the database of your monolith, and you establish your services that have been there from the beginning, now as more or less standalone solutions that are integrated with events and other, let's say, ways of integration that are suitable for bringing them together. And of course, one of the things, this is also mentioned here, that you do now on this path is, of course, that you clean up your domains. So we, in the beginning, saw, or you cleaned up your domains as part of this overall process. You saw in the beginning this matrix where we had orders, customers, and so on, which are widely calling each other. Now you have separated domains that maybe exchange events, maybe also call each other, but Via-Welt has defined service boundaries and domains that are reflected in those services. What can still happen, and probably this will also be the case for us, you might not drive this down completely to 0. Yeah, so of course, you have to reconsider all the time, how much does it cost me to elevate a certain functionality, to kind of rip it out from my monolithic piece of software versus what is my gain. And for certain features that are barely used or very expensive to transform, it might still be valid keep them here in the monolith. Good. So this basically summarizes the three-step journey how we transform the monolith into cloud-native software. Now, just to conclude, basically this is a quite hard journey, and we believe, or the industry also believes, that this can only be approached if you do it iteratively. As I just explained, it's also from use case to use case or scenario to scenario always a trade-off decision that you need to make, what you keep there, what you take out. The most relevant and most benefiting capabilities in the cloud should of course be the ones that you move out, and also those which kind of have a high speed of innovation, or also requirements that require to change should be the ones that go out, because those are the ones which you can then, with the help of continuous delivery, DevOps, like explained in the beginning, make successful. Good. Now let's come, or questions at this point. Yeah.
Do you recommend this three-step process for any other application? First develop as monolith to microservice?
Yeah, I think this is the general idea. So probably, I mean, it's always hard to generalize those approaches, right? Probably you need to look into what do I have. I mean, there might be certain special conditions in a certain scenario that require you to do something earlier or later than it is generally recommended. And I think this is also not like an algorithm, right? It's rather an idea, like what is something I try to do rather early, and what are things that I try to do rather late. But I think the general idea more or less is applicable to many scenarios. And, as I said, if you follow the links below there, even the titles of those steps, we took them now from general recommendations from Martin Fowler, who's very famous in the architecture domain. We made similar experiences, and later on found that he described it in that way, and we attached to what he wrote. I believe that many others probably can do it the same way. But of course, it depends on an individual case, or maybe you have something in mind. It doesn't.
Why not reconstruct it from the beginning? I mean, why decoupling it? Isn't it difficult to decouple?
Yeah. I think the problem is you have code, and it's not a little bit of code, but rather like thousands of people building code for decades, or working on code for decades. It's the functional spectrum is incredibly high. The complexity is incredibly high. So I think I was not part of this SAP Business by Design experience, but I think the problem is by the time you have reached, let's say, a little bit of the functional scope of the previous ERP, already so much changed, but you were busy just re-implementing it, right? That more or less what you achieved kind of already lost again in value. So it's always a continuous innovation that takes place, and by picking the right parts and focusing on where you have the biggest benefits, you don't run into the risk that you kind of just too unfocused, so just try to bring everything in. Yeah. Okay, so you can generate early success, also economically, technically, and then pick the next battle. Incorporate the learnings. Yeah? So I think that somehow makes it I hope it makes it somehow tangible. It's just the problem size which is big. Yeah.
Now that you have moved from monolithic architecture to microservices architecture, how has the scope of monitoring the infrastructure or even configuration management changed from that architecture to a new architecture?
Yeah. So I'm not sure if I understood everything, but of course now monitoring and observation of the state of the software, also troubleshooting is of course way more complicated. Yeah? Because by nature you have way more services that work together in order to fill, say, one request or one task. And of course you then need to establish tooling that helps you with that. Luckily there is tooling available for most of these challenges, like distributed logging, that you aggregate logs, for example. But still you need to somehow correlate, then you establish correlation IDs, for example. So there are many measures that you need to take in order to achieve, let's say, more or less a transparency level or a convenience level that you had before by definition, or just was just there, and now you need tools that can somehow help you with that. Or also perform, I think it's called distribute or application performance measurement and so on. So tools that give you metrics from the many nodes that are part of your environment. Yeah, you need some tools that help you to gain the necessary transparency. Otherwise, you lose the battle in just complexity and lack of traceability.
So, what is the price of the loose coupling? Imagine we have 20 microservices, and we develop each service independent of the others. Maybe we change the API or something like that, and how much pain in the ass is this to negotiate the available features so that our services are properly or are working the case as in the way they are expected to work.
I think it's not so hard to talk about what is the interface, because depends. I think we are also still learning. Yeah? But in most cases, I think it's quite simple to talk about what are the fundamental features of the service that you expect from something. And writing that down like, now this is my API spec, and this is what I more or less promise. Now let me do my job to implement this as best as possible. I even just have a case where we kind of avoid a lot of discussion on implementation details, but just saying, please tell me, what do you want? What is the quality criteria that kind of make it for you successful? And please leave it up to our team, so to say, to think about the how. So I think it's not necessarily always a problem increase, so it can even simplify things because it focuses discussions on the relevant parts. It allows teams to solve their problems in the way how they think it's best, but of course it also then establishes the accountability, which is also nice from a company perspective for the teams to be successful, because they cannot blame anyone anymore, like say, yeah, I had to use this framework, that's why it does not work, or I don't know, I had to wait for someone else to provide me something, which can of course happen if you still have services that build on each other, but it's less likely that these situations happen. So I think this is a simplification. I have not seen so many downsides, to be honest, so far. Of course, you have the price of distribution, that we just discussed. I think that where we are also still learning is sizing, in the sense of what is now the scope of a service. Is it now acquiring too much responsibilities or not? I think we see many extremes now, but that's something where I also cannot really state a conclusion from far away, because we have not seen the outcomes, so to say, of those projects for longer times to really judge are there now really big problems or not?
And in which dimension do you still support on-premises deployments? Is it just the database, or are virtual private clouds or something like that possible for the clients too?
Yeah, as I showed earlier, so we still support both.
Okay.
S4HANA has one single code line, and you can either run it on any premise, how we call it, like you would provide the infrastructure and take care of the life cycle of the product. You just buy the license and the software, so to say, from SAP. Or you buy it managed from SAP. But the product that you get, so the monolith, is the same, more or less. And yeah, and now what we of course want to do now, okay, here it gets tricky from commercialization perspective. You want to move more and more capabilities to the cloud, like RealSpend, what I showed. And what the customers now can do, for example, in the case of RealSpend, he can take his on-premise ERP, establish a VPN tunnel, so to say, to our cloud platform, and use the RealSpend functionality from the cloud. There he also has a cloud subscription that uses his on-premise ERP. So this is, so to say, the model. But we both still support both. And thanks to this standardized code line that just has different release cycles, so on-premise is usually a little bit slower, and also depends, of course, on the adoption of the customer, we can kind of make more or less stable assumptions.
One question, what is the main target here? I mean, decoupling the whole monolith into microservice architecture, or just go along with it? I mean, running both, or year by year decoupling the whole monolith?
Yeah, the idea is to achieve these qualities, right? The agility, elasticity, with it also the reduction of development and operational costs. And cloud is one way of getting to those qualities. As I said, you have to assess, does what I plan to do contribute to achieving those qualities? And based on this assessment, you then make such a decision. As I showed in the last step, some parts might really still remain due to technical or also commercial reasons in this monolithic part of the software, which, as we just saw, can be run on premise or in the cloud. Yeah, but if you run it in the cloud, of course, due to its large domain, you can leverage all the cloud principles. It's not the goal to bring everything into, let's say, cloud native services by the definitions that I showed you earlier, but a large part of it will probably in the long term be part of this transformation due to the reasons of the qualities that we look at. Someone who's looking for a binary answer, probably yes. More questions? Good. Yeah, then I have a little part on the last mile. I think we have 10 minutes left, roughly, right? Which I think fits quite well. On now, what happens if you have these microservices in place, and what kind of problems do you now face in this new architecture? Yeah, so what we used to do earlier was basically, we have this order service, we have a customer service in our monolith, and maybe we should actually attach the database to this application to show that it's kind of closely coupled. And what we can now do is, if we have a transaction, create an order, which maybe we want to check whether this order can be placed by checking some limits also that the customer has. We can basically read from the order table, select something into from the credit limit table, and then based on what I get, do something else. In this this is basically atomically isolated on this database. But if I have now a microservice landscape and I separated those domains, order and customer, into separate services that have their own persistence, of course this is not really possible anymore. Or I could do it with things like the two-phase commit, but the problem is two-phase commit basically favors consistency between services over availability. By doing that, it reduces the availability, and I usually want to design for availability, so two-phase commit is not really an option. It's also not really available in everything that I might use here as a database. And so I have to think about ways how I factor this into my design, that now certain parts of this overall architecture, in my case one of these services, can be down. And one way of doing this, for example, in microservices is implementing sagas. So this is here my distributed transaction, which covers service A, B, and C, based on a quite old pattern that was described in a paper from '87. You implement either a choreography or an orchestration over microservices where you run local transactions that do the corresponding database operations. You also try to make this, let's say, consistency boundaries always as big and self-contained as possible, but still you need to somehow connect them, right? And in case some of them, or one of them fails on the way, you always have a compensation operation that is implemented in one of the services, which then kind of compensates for the work that was already done, and kind of, I want to say rolls back, but undoes some of the work, or kind of hinders the failure. Yeah? And the implication is basically that you have to actively design for this failure. So you basically would have to implement a create order and check credit function in your services, but also one that if a failure, so to say, happens somehow explicitly, hence you cannot rely so much anymore on a database which would take care of a rollback. You have to think now, what do I do in such a failure scenario? And that's why the design pattern is called Saga. You have multiple steps, so to say, that complete your story when it's completely executed. If something goes wrong, then parts of it are undone. And another thing is, if you do too much synchronous integration in your microservice landscape, then you might end up with something like this. So it's basically a set of microservices that are integrated like a monolith with many point-to-point connections. Your interfaces look very much like the databases underneath those services. You may even have assumptions from those services, internals leaking out to other services. And that's then basically called a microservice monolith, which kind of exposes you to the problems of monolithic application architecture and distributed systems, which is kind of the worst outcome that you can get, because you move to distributed systems with the hope that you can gain, for example, agility and so on, which you kind of, at this point in time again lost. And you also don't have the advantages of a monolith, because suddenly network is also a problem for you. And what you do here to avoid this, or to kind of push back on that architecture direction, is basically that you try to inverse dependencies as much as possible, that you work, for example, with events. Instead of asking for information, you tell the overall system what is going on. and based on that, then other parts of the system start fulfilling their parts for the overall process. So yeah, as I mentioned, you use events, message brokers of different natures like queues, PubSub, or event lock message brokers, which are gaining more and more popularity. And then you can escape from this fallacy of running into the same monolithic architecture again. One more thing that is also getting more and more interesting for us is now, if you look at microservices, it's a way of kind of making logic, especially if you integrate them via events, making logic more and more infrastructure independent, just kind of focusing on what is actually the process that generates value for my end users. And if you take that to an extreme, you're basically talking about serverless computing. So where you don't provision infrastructure anymore, application instances, but rather provide kind of a certain logic, for example, to a platform that implements this serverless capabilities, and is then helps you to really virtually endlessly scale what you're doing. Based really with a scale down to zero, if nothing is happening, up until handling really large loads if it's necessary. What you see there typically is function as a service, so you provide a pure function in a programming language also that implements how you, for example, handle event that has been coming in, and backend as a service, which basically provides very scalable services on the database level, also for distributing information and so on, handling data streams in a distributed manner, and so on. And while we are of course working now on, while a lot of work happens now with microservices, this is of course something that is very interesting now in context of what we are doing, because it can also influence how we in the future build business applications. So now coming maybe back to your question, if you take it as a whole, your ability to react to such trends on the way and incorporate them also into what you plan, or what you're planning is of course limited compared to if you take it step by step. And for example, if we now start working on a new application, we can of course ask the question now, hey, there's this recent trend, maybe we can incorporate it into what we are doing with this application right now. Here's some book recommendations. So I think the first three ones, they're really good readings. So if you want to dive deeper into these topics, then feel free to have a look into them. Maybe one little information or a little advertisement slot in the end. If you found this interesting, or so if you want to, or if you can imagine to dive deeper into it, we are always looking for people that can help our team to manage this challenge that I just described. So if you're interested to learn more, just feel free to approach me, and I can help you to understand what kind of opportunities we offer. As you saw, it's a very nice working environment with a lot of benefits. I don't want to go through all of them. Nice technical challenges, quite, say, popular location in SAP organizationally as well as physically. So think about it, and I'm happy to hear from you if you want to learn more or have questions. With that, thank you very much for your attention. Also very much, thank you for the good questions. I liked it. So with that.